What if I told you that right now, there's a tiny but real chance that you could walk straight through your front door without opening it, and that this impossible phenomenon is actually happening billions of times per second inside your body? This is quantum tunneling, and it's one of those physics concepts that sounds like science fiction but is so fundamental to reality that without it, the sun wouldn't shine, your electronics wouldn't work, and you wouldn't exist. It reveals that the solid, predictable world we experience is built on a foundation of quantum weirdness that defies every intuition we have about how objects should behave. Here's the mind-bending reality. Particles can pass through barriers that classical physics says should be absolutely impenetrable. It's not that they go around or over the barrier. They literally appear on the other side without ever having been in the middle. Imagine you're playing pool and you hit the cue ball toward a wall. In our normal world, the ball bounces back. But in the quantum world, there's a small probability that the ball would just appear on the other side of the wall, as if the wall didn't exist. The ball doesn't break the wall, doesn't squeeze through cracks, it just tunnels through. This isn't a metaphor or approximation. Particles actually do this constantly. The math behind it is beautifully strange. In quantum mechanics, particles aren't little solid balls with definite positions. They're probability waves that spread out over space. When a wave encounters a barrier, most of it reflects back, but some of it can leak through to the other side. If you detect the particle on the far side of the barrier, congratulations, you've witnessed quantum tunneling. The probability decreases exponentially with the thickness and height of the barrier. For something as large as a person walking through a door, the probability is so astronomically small that it would happen maybe once in a time period much longer than the age of the universe. But for subatomic particles encountering atomic-scale barriers, it happens constantly. Want to see tunneling in action? Look at any LED light. The electricity flowing through it relies on electrons tunneling through energy barriers in the semiconductor material. Without quantum tunneling, modern electronics wouldn't exist. Your smartphone, your computer, even simple digital clocks depend on particles doing things that should be impossible. But here's where it gets really wild. The sun is powered by quantum tunneling. Nuclear fusion requires atomic nuclei to get close enough to stick together, but they're positively charged and repel each other with enormous force. At the sun's core temperature, nuclei don't have nearly enough energy to overcome this electrical repulsion. They should just bounce off each other forever. Except they don't, because sometimes they tunnel through the energy barrier instead of going over it. This allows fusion to happen at much lower temperatures than classical physics would predict. Without quantum tunneling, stars couldn't shine, and the universe would be cold and lifeless. Now here's the question that probably occurred to you. If particles can tunnel through barriers, why don't you fall through your chair? The answer reveals something profound about the difference between quantum and classical worlds. You don't fall through your chair not because the atoms are solid little balls that physically block you, but because of something called the Pauli exclusion principle. Electrons can't occupy the same quantum state, so when the electrons in your body get close to the electrons in the chair, they push back with what feels like a solid force. But here's the kicker, even this solid contact relies on quantum effects. The reason atoms take up space at all, the reason matter feels solid, comes from quantum mechanics, not classical physics. Quantum tunneling also explains why large objects seem stable while the quantum world appears chaotic. The bigger something is, the more particles it contains, and the more ways those particles can be arranged. The probability of all those particles simultaneously tunneling in the same direction becomes vanishingly small. It's like asking whether an entire crowd of people could all flip coins and get heads simultaneously. Possible in principle, but so unlikely that you'd wait longer than the age of the universe to see it happen once. This connects to one of the deepest mysteries in physics, the measurement problem. When you measure a quantum system, the wave function collapses and the particle appears in one specific location. But the act of measurement involves large numbers of particles in your measuring device, and somehow the quantum fuzziness gets averaged out into classical definiteness. Some interpretations of quantum mechanics suggest that tunneling events are constantly happening at microscopic scales, but they usually cancel out by the time you get to human-scale objects. You experience a stable, predictable world built on a foundation of constant quantum chaos. Here's something that will mess with your head. Radioactive decay is pure quantum tunneling. When a uranium nucleus decays, an alpha particle tunnels out through the nuclear force barrier. There's no trigger, no clockwork mechanism counting down to the moment of decay. The particle just randomly tunnels out when the quantum dice happen to roll the right way. This means radioactive decay is genuinely random, not just unpredictable because we don't know enough. Einstein famously hated this idea, saying God does not play dice with the universe. But quantum tunneling suggests that maybe God does play dice, and the randomness goes all the way down to the fundamental level. Modern technology is increasingly built on controlling and exploiting quantum tunneling. Scanning tunneling microscopes can image individual atoms by measuring tiny tunneling currents. Quantum computers use tunneling to create the superposition states that give them their power. But perhaps the strangest application is in biology. Some scientists think quantum tunneling might be involved in photosynthesis, helping plants transfer energy with remarkable efficiency. There's even speculation that consciousness itself might involve quantum effects, though this is highly controversial. So the next time you lean against a wall or sit in a chair, remember that the solidity you feel is an illusion created by quantum forces, and that somewhere in the microscopic world around you, particles are constantly doing impossible things, tunneling through barriers that should stop them, keeping the stars burning and your electronics running through sheer quantum weirdness.